Okay guys, next we will calculate the electric potential or potential from the electric field. Like if we know electric field, then we can calculate electric potential V. Similarly, if we know electric potential, then we can calculate electric field. These are the two ways through which we can calculate either E or V. And we have a proper procedure for that, and in this video I will discuss the calculation of potential. The calculation of potential If I use the word potential, it means electric potential, okay? V from electric field. E. And also differentiate the two terms. U. This U represent the potential energy. V represent the potential. The difference between potential energy and potential is that potential energy is equal to potential is equal to potential energy per unit test charge. This is the difference. Now we are going to calculate electric potential from electric field. Suppose we have a known electric field, and I represent it by a constant electric field, okay? Suppose we have a constant electric field. Like the electric field is time independent and space independent. It does not vary with time as well as with space, with point to point. Like the potential is constant point at every point, and also the potential is constant with the passage of time. And let's suppose this is the potential. This is the electric field. The electric field is time independent and space independent. Like it is independent of time and space. Like the potential is the electric field is constant everywhere on this point, at every point, and also it is constant with the passage of time. And this is the example of constant electric field. So it means that we have somewhere a positive charge here, because electric field originates from the positive charge and terminate at negative charge or at infinity. So it means that we have the positive charge somewhere here. But I'm not interested in this positive charge. I just need this electric field. Now suppose we are moving a test charge. We are moving a test charge from this point A. Let's say this is point A, yes, to point B, in the opposite direction of electric field. And also the test charge, we will always consider the test, and we are considering the test charge to be positive, okay? So this is my test charge, Q naught. Now the distance between A and B, this distance between A and B is L. I call it length L. Now the point charge is here. We are moving it in this way, in this direction. This is the displacement vector ds or dr. But this point charge, it's a positive charge, and this source charge or test charge is a positive charge, and also the electric field is in this direction. So there is a force on this test charge. Its direction is this one, and the force is represented by Q naught times E, which is equal to the force. Now in order to moving the test charge from point A to point B, we are doing work. So the work done in moving the test charge from point A to point B in a uniform electric field is equal to force times the displacement, the dot product of force and displacement. If we look at here, the displacement is in upward direction while the force is in downward direction. So it means that the angle between force and displacement is 180 degree. So from this we got minus FL, work from A to B. But we know that, as I already mentioned here, that the force is equal to Q naught times E. Since force is equal to Q naught times E. So the work done in moving a test charge from point A to point B is minus Q naught E into L. Now, this work done is stored in the form of electric potential energy. That is, the work done is stored in moving a charge from A to B is equal to change in potential energy, delta U. Now, but there is a negative sign, I think. There is a negative sign also. So delta U must be equal to minus work done and moving a charge from A to B, or delta U is equal to minus, one minus is this, one minus is there, so it's a plus time Q naught E into L. Now the potential difference, this is the potential energy, okay? This is the potential energy, or difference in potential energy, difference in potential energy. The potential difference will be the potential difference, which I represent by delta V, which will be equal to the difference in potential energy, delta U, per unit test charge. If I call it, let's suppose this is equation 1, this is equation 2, no, this is equation 2, this is equation 3, this is equation 4. Then using equation 3 and 4, we have, if we put equation 3 and equation 4, we get what we get is delta V is equal to delta U value is this one, which is Q naught EL over Q naught. Q naught cancel with Q naught, so we left with delta U, delta V is equal to EL. Delta V is basically, it's itself equal to VB minus VA, which is equal to EL. Now this is the case when we have a constant electric field. Now from this equation, we can write E is equal to delta V over L. E is represented in the unit of volt and length is represented in the unit of meter. So we have another unit for electric field, which is volt per meter, while previously the unit we used was Newton per coulomb. From the definition of this one, E is equal to force per unit test charge. So it means that volt per meter is also a unit of electric field, and both these are related with each other. We can convert volt per meter to Newton per coulomb. So this is in an assignment. This is an assignment. Convert volt per meter to Newton per coulomb. Convert volt per meter to Newton per coulomb. It's very easy, simple, so do it by yourself. Now this was the case when we have a constant electric field, but normally the electric field is not constant. Suppose if I have a charge, test charge Q, then the electric line of force originate from it in different directions. So if we look at here in this space, then the electric field is not constant, because electric field is stronger here, and then it becomes weaker and weaker and weaker away from this charge. And also at this point, in this region, we have a strong electric field. If we move away from this point, then the electric field decreases. So it's a space dependent and time dependent electric field. So if we have such a case, then how we can calculate the electric potential? So for that, I will consider a non-uniform electric field. Suppose this is a non-uniform electric field. It varies with space and time. And suppose we are moving a test charge from point A to point B through this non-linear path. Now, suppose the charge is somewhere here. This is the test charge, okay, positive charge, Q naught. Now here the electric field, the electric force direction is this one. This is the electric force, which is Q naught times E. And the displacement direction is this one. So here we have the angle, which is theta. Now in order to find the work done in moving the charge from A to B, the best way is to divide this charge, this path, into small pieces. And then we have to calculate the work done in each individual path, individual pieces, and then we will sum up those individual work and get the total work done. Like, we have to divide this path into small pieces or slices. So we have to calculate W1, W2, W3 up to, let's suppose we have 10 slices or 10 pieces, Wn. Then we can calculate the total work done from A to B, which will be equal to W1 plus W2 plus up to Wn. This will be equal to sum over I started from 1 up to n into Wi. We can replace it by the integral. Okay, this summation is replaced by this integral, and the integral is from A to B, and we have the work done dW. Okay, we can replace the work done from A to B is equal to integral from A to B f dot ds, because we have a small displacement here. It is represented by ds. Now force is equal to Q naught times E. Using this here, we have Q naught times integral from A to B E dot ds. This is the work done in moving a charge from A to B in a non-uniform electric field. Electric field is non-uniform, so I cannot bring it outside of the integral. So this means that the potential energy delta U the potential energy, I call it potential energy PE, is equal to delta U, which is equal to minus work done from A to B. So delta U is equal to work done is this one minus Q naught integral from A to B F dot ds, E dot ds, sorry. And the electric potential is, the potential differences, electric potential differences difference is delta V, which is equal to change in potential energy delta U divided by discharge Q naught. Now delta V is equal to, using the value of delta U, this one, we get minus Q naught integral from A to B E dot ds over Q naught. Q naught got with Q naught. So we have delta V, which is equal to minus integral from A to B E dot ds. Now this is the line integral, okay? This is line integral. Now this is the case when we have a charge which is moving from point A to B. But normally we are considering the reference point to be at infinity. Like A is at infinity. So the potential, electric potential at infinity will be equal to 0. So if this is the case, then we have delta U, which is delta V, sorry, which is, I call it ordinary point Vp minus V infinity. Like I am bringing the charge from infinity to point P. Here the potential is V infinity, which is equal to 0, and here the potential is Vp. So the change in potential delta V, which is Vp minus V infinity, which is equal to minus integral from minus integral from 0 to point P, and we have E dot ds. Now this is 0, so we have Vp, which is integral of minus integral of 0 to P E dot ds. This is the value of electric potential at a particular point P when the field is not uniform. Now we know that if I calculate the value of, like, we have a fundamental theorem of gradient. Let's say that if you have Vb minus Va, which is equal to integral from A to B del V dot ds. This is a fundamental theorem. I will prove it by considering the right hand side. The right hand side is from A to B, integral from A to B del V dot ds, where V is the scalar, it's a electric potential, okay, it's a scalar quantity. So we have this integral from A to B, and del times V can be written as partial V over partial x into I plus partial V over partial y into j plus partial V over partial z into k. And to ds, it's a vector, differential vector, so it can be written as dx into I plus dy into j plus dz into k. Now if we take the dot product of this with this one, we get integral from A to B. We have partial V over partial x dx plus partial V over partial y dy plus partial V over partial z dz. This can be written as integral from a to b v of x, y, z, dv of. We can write it as, I can write it here. This can be written as dv x, y, z. Here we have the integral from a to b. So differential of v is basically, integral of differential of v is basically equal to v. And the integral is from a to b, which is equal to vb minus va. So vb minus va is equal to this vector, so which is this one. Here we have this relation, like vb minus va is equal to integral from a to b del v dot ds. Also we know that vb minus va is equal to integral minus integral from a to b e dot ds. I have this value, delta v. Delta v is basically vb minus va, which is equal to minus integral from a to b e dot ds. So I put this value here. Now comparing these two equations, we get minus integral of e dot ds from a to b is equal to integral from a to b del v dot ds. Now I can write it as integral from a to b e dot ds. I bring minus sign to this side, so this is equal to integral from a to b minus del v. I bring minus to inside of this dot ds. Now these are both line integral, and we have this ds here, so it means that this e is equal to, this implies that E is equal to minus delta V. We can say that electric field is equal to the negative gradient of a scalar, and the scalar is electric potential. This is the fundamental theorem. So this is all about calculating potential from the electric field. While the calculation of electric field from the potential, we will do it later, might be after a few lectures. Thank you. I will share the assignment on the WhatsApp group very soon. Thank you.